Okay, so yesterday we started our unit 1 about equilibrium and equilibrium constants. We defined equilibrium, we defined dynamic equilibrium, the fact that it's always changing. Although we don't see any change in concentration, there is constantly a reaction happening forward and backward. Okay? And so we come up with the equilibrium expression of products over reactants. The square brackets mean the little values, little c, little d, little a, little b mean the coefficients, the balance numbers. And then we plug it all in, numbers, 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 and we can get KEQ, constant at equilibrium. What are our units of K? Changes, dependent on?
What units cancel.
Right, what units cancel in these concentrations. If it's squared, if it's the power of 1, if it's not there. What don't we include in our equilibrium expression? Solids or liquids, unless it's all solids or liquids. And what would we call that kind of reaction? What's the new word that we learned on the definition sheet?
Homogeneous.
Homogeneous equilibrium. So if it's a homogeneous equilibrium, we would indeed include all of them. Okay? And then we were doing a bit about, I got you just to figure out I got you to figure out the percent yield yourself because it's a Chem 20 concept anyway. And it's the same thing as your percentage that you get on a test. The only difference is that it feels different because you're talking about theoretical yield and experimental yield and maximum yield, and they feel different. But actually the maximum you could have got on that quiz I just handed back was 15. What you actually got was 12. And so your percentage is 12 out of 15. That's the same thing. And percent error would have been the 3 you errored on divided by 15. Okay? And this, though, we didn't talk about yesterday. So if you can read this reaction left to right and right to left, right, that's what those funny arrows mean, left to right and right to left, then the reverse K and has a K value, and the forward K has a K value. So do you remember, I'm just trying to get my pen to work. Not yet. There we go. When we flipped the reaction with delta H, what did we do with the delta H value? It became negative, or if it was already negative, it became positive. What about voltage in unit 2? If I flipped the reaction on those data tables with the voltage, what did I do to the sign? It changed from negative to positive or positive to negative as well, right? This is not the same, but it's one of the things you're going to get mixed up. So if I'm not reading it this way anymore, but rather I'm reading it this way, one would think that I would do the same thing if it's negative, positive, positive, negative. But that's not what happens. Because the way to calculate it is products over reactants. It's not about the delta H, it is about this. And so therefore, if I'm reversing the reaction, I'm now going up that same hill, the same waterfall, but I'm going up now instead of down. So the height is still the same. So instead of positive, it becomes negative. Instead of negative, it becomes positive, because it's still the same hill. The voltage potential is the same idea. You're going up a potential or down a potential. It's still about a waterfall. Whereas this is different. It's products divided by reactants. So if I'm reading it this way, I now have my products on the bottom and my reactants on the top. So it's the inverse of that fraction. And so therefore, the relationship is the inverse of it, the reciprocal. Does that make sense? So we can't flip the sign because it's not about a waterfall anymore. It's about the concentration divided by a concentration, numbers divided by numbers. So because we have this quotient, divided by, we have to flip it. Does that make sense? So if they've given you the K value for the one direction, you can just take 1 over that K value for the opposite direction. Okay? Yes?
So if it you'll know then, they'll have to give you like information for one side, so then you'll know that that's the K value for that side and the inverse of that.
That's right.
They won't ever ask you like find the K value of a certain side to find the other side. Is that even possible? You know what I mean?
If they gave you the concentrations, then they could. Like actually told you it was 5 moles per liter and 1.2 moles per liter, and then you could tap it into your calculator and find it.
But it would tell you if it's for the product or
That's
the reactant.
Yes, they'll tell you, when they state a K value, it's for the direction that we normally read it. Okay, so this K value is stated reading this left to right. So if they were asking you, right, what's the K value of so if this is decomposition, I suppose you could think of it as. If they asked you, what about the formation, then you would go 1 divided by. Okay. So, and then again, I've made a comment down here about the solution being mostly molecular. How do I know it's mostly molecular? How do I know? Well, in this solution, you got more of this, you got lots of this, and very little of this. Plus plus is shorthand for lots, and writing notes. Plus plus means a lot or very much or whatever. So I got plus plus, CH3COOH, and very little H plus and CH3CO minus. How do I know that? Because it's a weak acid, okay? What did we learn yesterday about what the numbers of K tell us? Do you remember? If it's really low, it favors the reactants. So is this pretty low? Consider our -5. That means 0.000018. Right? That's a pretty small number. I wouldn't want my bank balance to be like that. So pretty small number, and so therefore that means that the products over reactants, in order to have a small number, this must be small and this must be large. And so if it's a small K value, these are favored. That's how I knew I have a lot of the compound together. Which means I have a very small amount of H plus, which is why it's a weak acid, not a strong acid. Strong acids have very large K values. Therefore, I have a lot of H plus. Therefore, my pH is very low, no matter what. Even if I dilute it, it's still very low. Okay? All right. So then we did these questions, and we did question 2 together. Right? We answered question 2 together. So let's answer question 4 then. Which you have time to work on, but we didn't have time to mark. So in an experiment at a high temperature, oh, why would they put the temperature bit in there? What's different?
The concentration.
No? Concentration won't change. Well, that's not true actually. I say that and then I'll tell you later that it does. So the K value. K values are different at different concentrations. Or I mean, K values are different at different temperatures. Okay? Like solubility is different at different temperatures. So you have to report the temperature. All right? Okay. So write the equilibrium equation and law for this reaction. So the equation bit will look like this. Hydrogen bromide gas is placed into a sealed container and decomposes into hydrogen gas and bromine gas. And to balance this, I need a big 2 there. So that's the equation bit. Oh, look what I did. Silly me. What have I done? Nope.
All the 2.
Have I written a balanced chemical equation? Yes. Is it balanced? It is? Yeah.
It is.
Balanced. Is hydrogen diatomic? H2? Yeah. Is bromine a halogen diatomic? Br2? Yes. I made one mistake. One mistake that's new to this unit. This is good for science 10. Right. So, because this is an equilibrium, I have to write equilibrium arrows, not a normal arrow. You with me? So that's like this new little, like everything else, normal science 10, but whoop, that's the bit you'll forget. Okay, and then the law goes like this. KEQ equals the concentration of my Br2 times the concentration of the H2 divided by the concentration of HBr squared. Hands up if you got that expression correct. Hands up if you didn't do this question at the end of the class yesterday. Okay. Questions on that? Do you know why I squared it? Because there's a 2 in front. Look, even Rachel understands, and she was new here yesterday. Good, let's move on then. So then they give us some concentrations, and we can plug it in. So KEQ equals the concentration of Br2 is 1.30. Oh, sorry, I mean 0.130. Can't read. Both of them, yes? In fact, I'll just do it this way. Divided by 0.2 for that one. So sometimes you'll see this, by the way. Right? Sometimes you'll see it written like that instead, because it's just the same value multiplied by each other. Everybody get that? If I don't mind which way you write it, I just want you to be able to read it both if it's the same thing for both ways. Not to get thrown off by if I put that down. And this is squared. This is squared. So I have moles per liter squared. Moles per liter squared. So what are my units?
Moles per liter.
No.
Over what?
No.
1 over. Liters per
Nothing.
Moles per liter squared divided by moles per liter squared. Don't have any units. Cancel, 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 cancel. No units. Don't have to have units.
That's crazy.
Ah, it's a whole new world. Okay, so tappity tap in your calculator, and what do you get?
I didn't know the calculating part.
29.34. Yeah, I got 0.2.
I don't know.
0.29. No units.
Did you sig thing? So what?
Sig figs, I have 3 sig figs. So let's do sig figs. 0.29 exactly?
No. 293.
I'll help you with the calculator. Okay. Everybody okay with yesterday's material? That should be review. Everybody happy? Okay. Right. So now, here's the thing though. If you were actually doing this experiment, okay, and you took some HBr gas and you put it in the flask, and some of it decomposed into hydrogen and bromine gas, all right? You would know how much you put in to that flask. You wouldn't necessarily know how much you got out. How much was at equilibrium. It's a harder concentration to figure out. You can figure out the concentration of Br2 formed because it's brown, and you can put it in these special colorimeters which shine a light through it and tell you how much that light's deflected or diffracted, and like tell you the transparency of it, basically. How transparent is it, a percentage. And you can compare that to known samples of known concentrations, and you can solve for the concentration of that at equilibrium. So you can have that, I've got that at equilibrium. You can have that, what I initially put in, but you see how they've given you concentrations of all of these at equilibrium. And we have to plug in the equilibrium concentrations in here. My point is that this was given to you because they did the math before it. So we are about to do the math before it, because I can know how much I put into the flask, but you actually have to do some calculations to figure out how much you have at equilibrium. It's not always given to you. And if it is given to you, it's because they've done the math. Okay? So, flipping down the sheet, it talks about doing it that way. So, you set up what's called an ICE table. Okay? Because it starts I, C, E, ICE. I for initial, C for change, and E for equilibrium. So initially, how much did I put in? How much did it change by? And then what must I have at equilibrium then? At the end of it, at the end of the day. You get that? Okay. So let's read the question. This is a esterification. Right, an esterification. So when that many moles of alcohol and that many moles of ethanoic acid reacted in a beaker, this many moles of ester produced at equilibrium. The total volume is 1 liter. Why have I told you the total volume? Because our K value is all about those square brackets concentration, so I've got to have moles per liter. So my ice table, I want it to be in moles per liter.
So if you had 2 liters, you have to divide everything by 2.
Correct. Now here I've got a lovely 1 mole per liter, or pardon me, I've got a lovely 1 liter solution, so therefore 7.7 moles in 1 liter is still 7.71 moles per liter. Everybody all right with that? So I set up this ice table by, first of all, you write the reaction down, okay, with equilibrium arrows, balanced, done. Then, secondly, I write the information, I write my ice table, ICE, and then I start plugging in the information. So initially, I had that, moles per liter. Initially, I had that, moles per liter. So that's also in the question. And then the last thing in the question is this 4.8 moles per liter of ester that was found.
Why do you put the 4.8 twice?
I haven't yet. By this point of reading the question and setting up my problem, I've only put the blue stuff down. Okay? And then I begin my work. So my work will be in 3. Maybe. Okay, you ready? So, if I started with no ester, because remember I'm pouring the alcohol, I'm pouring the carboxylic acid into my beaker. I started with no ester. Everybody okay with that? So I start with no ester and no water. I'm going to make it happen. And I produced 4.8. It must have changed by 4.8. Everybody all right with that? So I can plug that number in next. And then, because this is a 1-to-1 mole ratio, for every mole of ester, I must have also made a mole of water. So if I've made 4 moles of ester, I must have made 4 moles of water. And 4.8 moles of ester, I must have made 4.8 moles of water. So it must have also changed by 4.8, and at equilibrium, it must be 4.8. Everybody okay with the green bits?
Why is
Abby?
it positive 4.8?
Because I added 4.8. Or I didn't, the reaction made 4.8. Didn't take it away, didn't react it, it added it, produced it. Okay, all right, so that's the first bit of thinking. The second bit of thinking in yellow then is this. If I made 4.8 moles, and for every 1 mole of this reacted, I produced 1 mole of this, I must have reacted 4.8, or used up 4.8 to get the 4.8. And same thing here. This is because they're all 1-to-1 to 1-to-1 mole ratios, and so therefore, if one of these and one of these produce one of these, and you're saying you produced 4.8, then 4.8 and 4.8 must have reacted to produce the 4.8. Everybody okay with the yellow?
And you don't have 7.37, 7.71 on the right side on the top because there was only 1.
Because when, no, you mean here? Why don't I have the 7 numbers here?
Yeah.
Because this is saying I poured alcohol and poured carboxylic acid. I did not pour any, no ester, and I did not pour any water into it. Okay? And so if I started with 7.71 and I reacted 4.8 of it, then I must still have 2.91 at equilibrium, and I must still have, do the subtraction, 2.57 in equilibrium. And now you know your concentrations of all of them at equilibrium. And so, any questions on the yellow? And so then my equilibrium box numbers get plugged in to that equilibrium equation, products over reactants. Bless you. And so tappity tap tap tappity tap tap. 3.08, no units. Pretty large K value. Pretty large K value. What does that tell you? Large K value? Products are favored. That's good when you're in the, do you know what? I dropped my whole bottle of perfume today. The whole big glass smashed. My room stinks. There's shards of glass everywhere. I don't know what it's called. It's expensive. It's alright. Beauty free this summer. So if I smell today like perfume really strongly, it's not my fault. It's my smashed bottle of perfume. But the point is, if you're in the perfume making industry and you're trying to make this ester to go into your perfume, so far you're pretty in favor. You're making your ester, you've got a lot of it made. You're happy. Tomorrow we're going to learn about how you can make even more of that ester, so that you can get this number to be even higher. Okay? All right, so products are favored, and that's it. Okay. So, oh, there, look at that, I even put little steps for you as I discussed it. Look at that, that's pretty clever. Done. Okay, answer with units will be different each time. All right, so here's another question. This one's a little bit trickier for a couple reasons. Number one, it's a 1:1 to 2 ratio. Okay, so it's the first tricky bit. And the second tricky bit is they have here all these different systems. So it's saying you got to do this question 3 times. You got to do that question, and find the K value. And then you're going to do the second and find the K value, and then you're going to do the third and find the K value. And all your K values should be the same, regardless of whether I chuck just those 2 things and wait to see what happens, if I chuck 3 things and wait to see what happens, or if I just chuck the final product in and wait to see what happens. Your equilibrium, the point they're trying to make, is the equilibrium ends up being the same. If you fill your bathtub full of cold water and wait, it'll go to room temperature. If you fill your bathtub full of hot water and wait, it'll go to room temperature. If you fill your bath water full of hot and cold and wait, it'll go to room temperature. That's what this is saying. No matter which way you start with, your reaction still reaches equilibrium. Okay? So, do you want to do it together? Is the first one anyway? Okay. So where do we start?
No.
Write down the reaction. I'm just going to flip up so we've got a bit of notes in millimoles per liter. I hope that doesn't scare anybody. Right, so how is it thinking? H2 plus I2 equilibrium to HI, all gases. Then what do? Right ice. And I like to put this bar here so that people remember to subtract or add to go to the E. Right, just like we did in primary school or elementary school. Okay, so system 1. So we're just looking at this, right? Oh, equilibrium concentrations. It's given it to you.
Yeah.
Yeah.
They're not fancy. All of them?
Mm-hmm.
I just solve the K value, make sure they're
I think I meant to delete some of those for you. They are all there. Okay, let's set up an ice table for the first one, and then we won't do the rest. Okay, we'll just do the K value for the rest. Okay, so what's the initial concentration of H2? 1.00. The initial concentration of I2? 1.00. And the initial concentration of HI? 0. The equilibrium concentrations have been given to you already, but let's just pretend they haven't given you these 2 for a second, and figure out how they calculate those. Okay. I've got some questions in your textbook that you're going to do on practice problems, so you'll have a proper practice with ice tables. So the equilibrium concentration of HI is 1.56. Everybody hear that? So how much did it change by? 1.56. Did I make it or use it up? So I've added 1.56 to the system. Okay? Now, keeping in mind 1 to 1 to 2 ratio. If I added 1.56, how much must I have taken away of my I2? Half of 1.56. So, for those of you that are still like, whoa, where'd you get that from? This is like when we are doing our normal stoichiometry in Chem 20 and we cross to the other column, we have to use the bridge. So if this is how many moles, although it's not, it's moles per liter, but, and I'm crossing the bridge to this system, I would say it's times, you guys seem to use times where you're going divided by where you've come from, right? And so therefore it's that divided by 2 or times 1 over 2. Okay, so that's how this ties in with stoichiometry. It's about your mole ratio. And so this as well as 1.56 divided by 2, which I certainly hope is, once you finish subtracting these, you get 0.22 and 0.22. Is that true? 1.56 divided by 2, 0.78, and 1 subtract 0.78 is 0.22. Okay? And how do I figure out KEQ then? Products over reactants, so you write down square bracket HI squared divided by H2 times I2. So I have 1.56 squared divided by 0.22 squared.
Why is that?
Craig, put your phone on my desk.
Why is there 2 on the I up high?
Why is the 2, this one?
No, below. Like why is the
Oh,
I?
that's why. I was thinking ahead. I was thinking ahead to this square. That's just my penmanship. And tappity tap tap your calculator, what do you got? Not you. Yeah. What do you got? 50.23.
Well, 2.8, but
28, so 3. Units?
liters per mil. Oh, no, nothing.
Nothing.
Above square.
Nothing. And you should get approximately 50 and approximately 50 for all of these. Even though they're all different concentrations, the same equilibrium constant. The quotient is the same. The numbers are different, but the quotient is the same. Okay? For example, there's many ways to represent 1/3. Right? You could go 2 over 6. Still be 1/3. For example. And then there's many ways to make up that 6. You could go 1 times 6, you could go 2 times 3. And it'd still be 6 on the bottom. And you'd still have 1/3. Okay? So there's many ways to make up that quotient number, that K constant, but it's so different numbers to be plugged in, but the same K value. Yeah.
If there's a percent error, like would you have percent error between those 3 if they're different?
No, you would have a range. So it wouldn't necessarily, because you can't compare percent error unless you know which one is the right one. You can compare percent error to a book value, a data booklet value, right? But not within each other. You just have a range,
Okay.
which then shows how the validity of your experiment as well, right? You should have as narrow a range as possible. So it is an indication of something, but not percent error. Yes.
Will we always be adding to the solution on the right-hand side, or if it was a decomposition, would it be?
No, we're gonna, for example, in this situation, right, let's cross out those values, let's cross out that value, it would be decomposition. And you have to see how much you're forming of those.
Okay. But you would still be adding that.
Yeah, it's still the
on
same kind of ice
so
table.
to a solution.
You bet, you bet.
If you did have that,
Yeah.
would you subtract the
Would you like to do the number 3?
kind
Should we do number 3? Okay, so let's say they give you the information on number 3, but they've scratched out that one I've scratched out for you. Okay? So, let's get this a little bit bigger. Okay, so, number 3. Initially, in fact, this is more likely the situation. They wouldn't give you this either. Okay, so the question's telling you that these two things are reacting and forming that. And initially, I have no H2, I have no I2. I start with 3.20 millimoles per liter of my HI. And at equilibrium, I find 0.35 millimoles per liter of my H2 gas. Okay? So that's more like the equation. And then it says calculate the KEQ for this reaction. So you set up the ice table, it looks like this, and then you have to think about your changes. So this is what I have at equilibrium. How much did it change by?
added 0.35?
I added 0.35 to the situation. And if I made 0.35 of that, I must have also made
0.35 iodine.
0.35 of the iodine. Okay? Or decomposed into, doesn't matter. And so therefore this is also 0.35. And I must have reacted how much I2 to do that? 0.7. Because it's double. So 2 times 0.35, which equals 0.7. And I must have reacted it up, used it up, so I'm subtracting. And so the difference in those is 2.5. Help me out.
2.5.
Is that what it says underneath the scribble?
Yeah.
Oh, that's handy. KEQ is the same HI squared over H2 times I2. And so it's 2.5. I was looking at the wrong number there. So therefore it's 2.5 squared divided by 0.35 squared. And top of the calculator? 51.0.
Yeah.
So is that pretty close to our other one? Yeah. So this is the exact opposite. I didn't add my H2 and I2 and wait. This time I added my H2 and waited. HI I mean. I had my HI and waited. And it ended up going the other way. And I have the same K value.
So would that make the H2 and I2 your products?
Your products are almost irrelevant. So in terms of the situation, yes, I produced H2 and I2. Okay? In terms of the way this is written, no, I am producing HI. Because remember, at the very first instance, I produce H2 and I2, but then what happens to that H2 and I2 that I've just made? It's going to move back and produce the H2 back again, or HI I mean. And then the HI I've just made decomposes. And then that stuff, and then that stuff, and that stuff, until it's all done. So this is more like a bathtub being filled from one end. So if I pour the bucket of bath water into one end, like, I mean, really chuck it in, that's right, it's going to splosh this way, producing my H2 and I2. Too much of it, actually, right? Because it goes up onto that side of the bathtub. And then, what does it do? Splashes back again. Then H2 and I2 react to make HI. Oops, a bit too much. And then it splashes back again, but it's not as much this time, but still too much. Not as much, but still too much. Until eventually, the bathtub reaches equilibrium, a flat value, where the concentration, or the height of the HI is the same as the, or isn't the same, remains constant, and the height or the concentration of the H2 and I2 remains constant. However, it's still reacting, still splashing underneath the bathtub, underneath the water. You just don't see any change, but underneath there's still that going this way and this going this way. Okay, dynamic equilibrium. Okay. All right, so at the bottom of this, I think I've put a practice problems. Did I list them? Yes. So on page 644,
Junior class change.
in your textbook, if you haven't brought a textbook, you can borrow one from the cover behind Lindsay. Please do these questions, because they're going to help you with your ice tables.